In the last class, we have discussed the lossless parallel plate transmission line. So here we discuss the lossy parallel plate transmission lines. A lossless parallel plate transmission line is characterized by two perfect conducting plates. So the conductivity of the conducting plates is infinity, separated by a perfect dielectric medium in between them. So the conductivity of the dielectric medium in between them is 0, or the loss tangent is 0. So this corresponds to a lossless transmission line. So now losses will appear on the transmission line due to two reasons. One is the conductivity of the conducting plates is not infinite. That means the conductors are not perfect, sigma c not equal to infinity. And second reason is that the dielectric medium in between them is not a perfect dielectric medium. That means sigma not equal to 0. Sigma is very small for the dielectric medium, but it is not 0. So, the loss tangent is non-zero over here. Loss tangent sigma by omega epsilon is non-zero here. And for the conducting plates, the conductivity is not infinite, but it is very high quantity. And we have already seen that a lossless parallel plate transmission line is characterized by capacitance per unit length C and inductance per unit length L. So, but in order to characterize the lossy parallel plate transmission line, we require two more parameters: the conductance G per unit length and the resistance per unit length of the plate conductors. So the conductance per unit length is measured in between the plates, and the resistance per unit length is measured for the conducting plates. So for a lossless parallel plate transmission, G and R are zeros. So they are entirely characterized by C and L. But a lossy parallel plate transmission line is characterized by C, L, G and R. So first of all, we will calculate the conductance per unit length G. For that, assume a dielectric medium having non-zero conductivity or non-zero loss tangent. And we know that the capacitance of this conducting medium is equal to C is equal to Q divided by V. So we already know that Q is C times V. From that, C is equal to Q divided by V. So, but from Gauss's law, we know that closed integral E dot ds is equal to Q by epsilon 0. Or in terms of the displacement vector, this can be written as closed integral d dot ds is equal to Q. But for the dielectric medium having a permittivity epsilon, we know that D is equal to epsilon times E. So for the medium, this equation reads Q by epsilon, and therefore D is epsilon times E. So closed integral epsilon E, epsilon can be taken out, E dot ds is equal to Q. So we can substitute this value of Q over here, epsilon closed integral E dot ds divided by, so we know that the potential is the line integral, negative line integral of the electric field, negative line integral E dot dl. So this is the capacitance of the dielectric medium. So since the dielectric medium is having a conductivity sigma, then the current density is equal to sigma E. So that means J and E are parallel over here. So this is nothing but the Ohm's law. For a perfect dielectric or a lossless dielectric medium, sigma 0, and therefore the current density J is also 0. But here J is non-zero, and there is a finite resistance for the dielectric medium between the two conductors. And we know that according to Ohm's law, this resistance is equal to V by I. So V is nothing but minus line integral E dot dl. And we know that I is equal to integral J dot ds. So here J is sigma times E, which is integral sigma E dot ds, where sigma can be taken out. So this is equal to sigma integral E dot d. Yes. So substituting this over here, we get sigma into integral E dot ds. So now we have to multiply this expression, which is termed as 1, with this. So then we get 1 into 2 gives RC is equal to integral E dot dl minus integral E dot dl is there in the numerator. Here it is in the denominator. So that two terms cancels, and we have RC is equal to epsilon integral E dot ds by sigma integral E dot ds. So this integrals cancel. So this is equal to epsilon by sigma. So R into C is equal to epsilon by sigma. So we know that the resistance is the reciprocal of the conductance. So R can be written as 1 over G, where G is the conductance of the dielectric medium in between the plates. Writing R in terms of G, will get C divided by G is equal to epsilon by sigma. And from that, G is equal to sigma by epsilon times C. So once the capacitance per unit length is known, the conductance per unit length of the dielectric medium between two conducting plates can be easily calculated. So we have already calculated the capacitance per unit length of the transmission line, which is equal to epsilon W by D. So substituting the value of the capacitance per unit length, the conductance per unit length is equal to G is equal to epsilons will get cancelled, sigma W by D. So since this capacitance is measured in farad per meter, the conductance is measured in Siemens per meter. So for the transmission line, the capacitance is measured in unit length. So here G is also measured per unit length. So this R and G are for the dielectric medium. So now we can calculate the resistance per unit length of the conducting plates. So we have seen that the conducting plates are having a very large value of conductivity, but it is not infinity. So they are not perfect conductors. So there will be losses due to this conductors also. Losses may arise due to two reasons. One is due to the non-vanishing loss tangent, and other is due to the imperfect conducting plates. So the conductivity of the conducting plates are represented by sigma C, and sigma C is very large. Since sigma C is a finite quantity here, ohmic power will be dissipated in the conducting plates. The ohmic power dissipated is equal to the average power per unit area dissipated in each of the conducting plates. So the average power per unit area. So power is having no dimension, and the area as a vector quantity, which is always normal to the surface considered. So the power per unit area should be along the direction of the area vector. So since power is dimensionless. So for this transmission line, we can see that the area is along the y direction. So power per unit area should be also along the y direction. That means the average Poynting vector, which is equal to the average power per unit area, should be along the y direction. So the average Poynting vector should have a y component if the conductivity of the conducting plates are finite. I've already learned that the average Poynting vector, which represents the average power per unit area, is equal to half into real part of E cross H star. So here we have already seen that the electric field is along y direction and the magnetic field is along x direction. So E cross H star is y cross x. So that is along negative z direction. So that means the Poynting vector is along negative z direction. So if the electric field exists only in the y direction, then the average Poynting vector should have a z component only. So for the average Poynting vector or the power per unit area vector to have a y component, the electric field should have a non-vanishing axial component or z component. Electric field in axial direction, transmission line in the propagation direction, axis along z direction, ഒരു component ഉണ്ടെങ്കിൽ മാത്രമേ average Poynting vector ഒരു y component ഉണ്ടാവുള്ളൂ. So suppose the electric field has a very small but non-vanishing, non-zero z component, axial component, which is az ez. Then the Poynting vector, average Poynting vector, is equal to half into real part of az ez cross ax hx star. So az cross ax is ay. So it has got a y component, provided there is an electric field along the z direction or along the axial direction. So if the conducting plates are having finite conductivity, there should be an electric field, even though it is small, in the axial direction also. In addition to the electric field along y direction, there should be a small electric field over here, so that the average Poynting vector has got a y component, which equals the average power per unit area dissipated in each of the conducting plates. So now, in order to calculate the resistance per unit length, consider the upper plate where the surface current density is having a magnitude as that of the magnetic field. We have derived this in the last class. Now we define a quantity called the surface impedance of an imperfect conductor. So ZS. which is defined as Zs is equal to the ratio of the tangential component of the electric field to the surface current density at the conductor surface. The tangential component of the electric field to the surface current density at the conductor plate. So the Zx is defined for an imperfect conductor. So we can define Zs for the conducting plates. First of all, we can define it for the upper plate. So for the upper plate, we know that Zs is equal to a tangential. Tangential means tangential to the uh, propagation direction or the axial direction. So Zs is equal to Ez. E tangential is Ez over here, uh, divided by Js is Js for the upper plate. Surface current density for the upper conducting plate, which is equal to Ez by Hx. Jsu is having the magnitude of the magnetic field. So Ez by Hx should be equal to the impedance. The ratio of the electric field to magnetic field is the intrinsic impedance eta C. So we use a suffix C to represent the intrinsic impedance of the conductor. So eta C is due to the imperfect nature of the conducting plates. So if the conducting plate is perfect, Ez, the Z component is 0 and therefore eta C equal to 0. So Ez is there so that the average Poynting vector is non-zero. Even though the conductivity sigma c of the plate is not infinite, it's a very large quantity, and we assume that the operating frequency is also sufficiently high so that the current flows in the surface layer, as we have studied in the skin effect, and therefore we define JSU, the surface current density. We don't consider the thickness of the conductor over here. So we consider it as a surface current distribution. And we have already learned the intrinsic impedance of a good conductor in our module, which is equal to eta c is equal to root of mu by epsilon c. So, we have found that it is approximately equal to 1 plus j into root of pi f mu by sigma. So, it has in the real and imaginary parts which are having equal magnitudes, and we also find that since the real parts and imaginary parts are equal, then the theta is equal to 45 degrees. So therefore the magnetic field lags behind the electric field by 45 degrees. So we have already discussed about this in detail, and eta c is equal to 1 plus j into root of pi f mu by sigma. So for our conducting plates, we have to represent sigma by sigma c and mu by mu c. So here sigma c represent and mu c represent the properties of the conductor, and sigma, mu and epsilon represent the properties of the dielectric medium in between them. So we have to use the suffix c over here. So this is the eta c, and we have find that Zs is equal to eta c, and therefore Zs, the surface impedance, is also equal to the intrinsic impedance. So 1 plus j into root of pi f mu c by sigma c. So we have already seen that the real part of the impedance is called the resistance, and the imaginary part is called the reactance. And now we can calculate average Poynting vector small p sigma as half into a real part of E cross H star, and And we have seen that it is along y direction, and this is produced due to the axial electric field Ez and the magnetic field along x direction. Here we can represent the axial electric field Ez in terms of the surface impedance. The surface impedance Zs is equal to Ez by Hx or Ez by JSU for the upper conducting plate. So Ez is equal to Zs into JSU, and Hx is already JSU itself, and the direction is always along y direction. This is along z and this is along x. So we find the magnitudes then. So half into a real part of Ay is here. Ez is Z into JSU multiplied by Z cross X is AY. The dot cross product is done over here. Then we just multiply the magnitudes. JSU. So AY cap on both sides cancel, and P sigma is equal to half into real part of JSU square. JSU into JSU is modulus JSU square into Zs. So this is a real quantity. So we can just take this as half into modulus JSU square into real part of Zs. The real part of the surface impedance is the surface resistance Rs. So we can write this as half into modulus JSU square into Rs. This is the ohmic power dissipated per unit area, which is the average power or the average Poynting vector. So now we have to calculate the ohmic power dissipated and the unit length of the plate. So we know that the conducting plates are having a width W and length is very large. We have a quantity, and therefore we are taking the quantities per unit length. So then the ohmic power dissipated per unit length of the plate having width W is equal to, so we know that P sigma is power per unit area. So we have to get power per unit length. So we have to multiply this with W. So this is area is W into L. So we have to multiply this by L, then we get power per unit length. So which is capital P sigma, power per unit length, or capital P sigma. So capital P sigma is equal to W times small p sigma. Small p sigma is the power per unit area, and capital P sigma is the ohmic power dissipated per unit length. So therefore capital P sigma is equal to half into modulus JSU square Rs into W. So we have to multiply and divide this equation by W. And we know that JSU is the current per unit length perpendicular to the flow of current, and therefore I is equal to JSU into W. So JSU square W square is equal to I square. So half into I square Rs by W, where I is equal to Js into W and I square is equal to JSU square into W square. So this is the ohmic power dissipated in the unit length of the plate. So this equation represents the power dissipated when a sinusoidal current of amplitude I flows through a resistance Rs by W. അപ്പോൾ ജനറലി നമുക്കറിയാം ഒരു കറണ്ട് ഐ ആർ എന്ന് പറയുന്ന റെസിസ്റ്റൻസിലൂടെ ഫ്ലോ ചെയ്യുമ്പോൾ ഐ സൈനസോയിഡൽ കറണ്ട് ആണെങ്കിൽ ആവറേജ് പവർ എന്ന് പറയുന്നത് ഹാഫ് ഐ സ്ക്വയർ ആർ ആയിരിക്കും. So this represent the power dissipated when a sinusoidal current of amplitude I pass through a resistance Rs by W. So here the effective resistance is Rs by W for the upper conducting plate. So the effective resistance per unit length for both the plates, for the upper as well as the lower plates, as the sum of these two resistances, and it is equal to R is equal to 2 into Rs by W. The effective series resistance per unit length for both the plates of a parallel plate transmission line having width W is equal to 2 times Rs by W. So we have already find Rs as the real part of Zs, which is equal to this root of pi f mu c by sigma c. So Rs is equal to root of pi f mu c by sigma c. The sigma c is the conductivity of the plate. So since this R is 2 times Rs by W, its dimension is resistance per unit length, ohm per meter. So this is the resistance per unit length of the two conducting plates. So we have defined the 4 distributed parameters of a parallel plate transmission line, L, C, G, and sigma. So the table gives the list of the 4 distributed parameters of a parallel plate transmission line having width W and separation distance D. So R is equal to 2 by W root of pi f mu c by sigma c. It is the resistance per unit length, and the inductance per unit length is mu into D by W, and the conductance per unit length is sigma W by D, and the capacitance per unit length is epsilon W by D. The unit of R is ohm per meter, and unit of L is Henry per meter, unit of G is Siemens per meter, and unit of C is Farad per meter. And we have also seen that the surface impedance has got a real part as well as an imaginary part. So the real part is equal to root of pi f mu c by sigma c, and the imaginary part is also equal to root of pi f mu c by sigma c. So the positive reactance is numerically equal to the resistance. So if we are taking the total complex power, ഇപ്പം നമ്മൾ പവർ എടുത്തതിൽ റിയൽ പാർട്ട് മാത്രമേ വരുന്നുള്ളൂ, ഹാഫ് ഇൻറ്റു റിയൽ പാർട്ട് എടുത്തത്, റിയൽ പാർട്ട് എടുക്കാതെ ടോട്ടൽ കോംപ്ലക്സ് പവർ എടുക്കുകയാണെങ്കിൽ ഫോർ ദി ട്രാൻസ്മിഷൻ ലൈൻ ദിസ് എക്സസ് വിൽ ലീഡ് ടു an internal series inductance per unit length, which is given by Li is equal to Xs by W. So Xs is having the same magnitude as that of Rs, so that is equal to Rs by W. So generally this internal inductance is negligible in comparison with the inductance per unit length L. So usually we neglect this, and generally we take the real part only. So the series resistance is only taken. And we have also seen that for the calculation of power loss in the conducting plate having finite conductivity sigma c. So we need an axial electric field Ez so that the Poynting vector exists in the y direction. So the electric field is there in the direction of propagation. So along the transmission line, the wave transmit along z direction, and for the lossless transmission line, we have taken that the electric field is along y direction and the magnetic field is along x direction. So, but in the case of lossy transmission line, in order to accommodate the averaging Poynting vector, we need a small axial electric field component. So this component shows that there is a component of electric field in the direction of propagation. So this show that the wave transmitting along a lossy transmission line is not strictly transverse electromagnetic. In a transverse electromagnetic wave, both electric and magnetic fields are perpendicular to the direction of propagation. Since there is a component of electric field along the propagation direction, the wave traveling along a lossy transmission line is not strictly TEM. So the existence of the axial component make the wave along a lossy transmission line not a TEM, strictly not a TEM. But this axial component is very small compared to the transverse component EY. So the propagation direction is Z, and along the propagation direction we have Ez, but the magnitude of Ez is very small compared to the magnitude of EY. So we can almost neglect this Ez, and we have to calculate the magnitude of the Ez first, and the ratio of the magnitude of Ez to EY. We know that Ez by Hx is equal to eta c, and Ez by Ey by Hx is the uh, intrinsic impedance of the medium. So Ez can be written as eta c Hx, and Ey can be written as eta Hx. So modulus Ez by modulus Ey is equal to modulus eta c by modulus eta. So hx will cancel. So we know that eta is mu by root mu by epsilon, and 1 over eta is root epsilon by mu into magnitude of eta c. Eta c is having both real and imaginary part, and we have seen that eta c is equal to 1 plus j root of pi f mu by mu c by sigma c. So a plus ib formula ആണ്, a plus jb formula ആണ്. അതിന്റെ മാഗ്നിറ്റ്യൂഡ് എന്ന് പറഞ്ഞാൽ root of a square plus b square ആണ് അല്ലേ. ഇവിടെ real part and imaginary parts are equal. Root of a square plus a square, that is root 2a. So magnitude of this eta c is equal to root 2 into a and b are equal root pi f mu c by sigma c. So we can write it as root of 2 pi f mu c by sigma c, that is omega mu c by sigma c. 2 pi f is omega mu c by sigma c. So substituting this over here, we can write epsilon into this omega mu c by sigma c, and there is a mu over here. Mu is the permittivity of the dielectric medium and mu c is that of the conductor. So since both are non-magnetic, mu and mu c is equal to mu 0, so they cancels, and we have root omega epsilon by sigma c, and this is a very small quantity. This is Ez by Ey for a lossy transmission line. So we can do one example of copper plates separated by air dielectric. For copper plates, sigma C is equal to 5.8 into 10 to the power 7 Siemens per meter, and epsilon is epsilon 0 itself. So substituting these values over here for a frequency of 3 gigahertz, and omega is just 2 pi f. So substituting these values over here, we can see that Ez modulus Ez by Ey is equal to some approximately equal to some 5.3 into 10 to the power minus 5. So that means Ez is 5.3 into 10 to the power minus 5 times Ey. That means Ez is very less than Ey, only 10 to the power minus 5 times Ey. So we can almost neglect Ez, and we can retain the designation TEM. So even though the wave along the lossy transmission line is not strictly TEM, it is only TM. Magnetic field is only transverse to the direction of propagation. It is not strictly TEM, not transverse electromagnetic. We can retain this designation TEM since the axial component Ez is very small compared to the Ey component, the transverse component Ey. So this is due to, in this expression we can see that sigma C in the denominator, sigma C being the conductivity of the conductor, even though it is not infinity, it is very large. So we can say that the Z by Ey is very small. So if the conductor is a perfect conductor, then sigma C is infinity and Ez by Ey is 1 over infinity equal to 0, Ez equal to 0. So that is for a lossless medium. For a lossless medium, the conducting plates are perfect conductors and Ez will not be there. So in such case, so in a lossless transmission line, parallel plate transmission line, the wave propagating is always transverse electromagnetic wave. But in a lossy dielectric medium, it is not strictly TEM, but we can regard it as TEM since the axial component is very small compared to the transverse component Ey. So the component Ez can be considered as a slight perturbation, and we regard the wave traveling along a lossy transmission line as approximately as a transverse electromagnetic wave, not a strict transverse electromagnetic wave. Okay, thank you.